Okay, so today we are going to talk about a new concept called molar mass. And molar mass is really, really similar to the atomic mass of an element and of a compound. So if I ask for the atomic mass, where can we find that value? Where do I find atomic mass? If I wanted to know oxygen's atomic mass, where can I find it? Can I find it on the periodic table? Yeah, right. I can find it right on the periodic table. And what is oxygen's atomic mass? Tell me the number. What's the value of oxygen's atomic mass? Oxygen is 15.999 or 16, right? Oxygen has an atomic mass of 16. And what's the atomic mass, the sum of? Protons and neutrons. Perfect. Okay. So atomic mass, right, is that bigger number on our periodic table. It's the sum of the protons and neutrons. And we know that it is a weighted average, right? We talked about that being a weighted average of all of the different isotopes of oxygen. Okay, do you remember what an isotope is? An isotope is atoms of the same element that have different, what? Neutrons. Good. Different masses, which means different neutrons. Okay. So we said molar mass is really similar to atomic mass. When I talk about the atomic mass of something, I'm talking about the singular atom level. Right? One single atom of oxygen weighs 16 AMU. Okay, but when I talk about molar mass, it's the mass of 1 mole of our substance. And so it's a much bigger scale. So I'm going to tell you what the difference is between these two things. Okay? The good news that for molar mass and atomic mass is that the value is the same. The actual number will be the same. The unit and the scale at which we look at that is different. Okay, so let's break down what this definition means. The molar mass is the mass which is measured in grams of 1 mole of our substance. 1 mole of our substance. Have you heard of a mole before? You know what a mole is? Not the animal, not the rodent. Okay? A mole in chemistry terms is a unit. Okay, so it's just like grams or kilograms or whatever. It's a unit. And what a mole is I want you to think about it similarly to the way you think about a dozen. What is a dozen of anything? How many is it? 12, right? So it doesn't matter if you're talking about a dozen baseballs or a dozen roses or a dozen donuts, right? All of those things mean 12, right? Dozen means 12 across the board. And so a mole is similar to a dozen, just on a much, much, much larger scale. So 1 mole of any substance, and you just abbreviated MOL, that's how you abbreviate mole. 1 mole of any substance is equal to 6.022 times 10 to the 23rd of any substance. So it's just a much bigger version of a dozen, right? A lot bigger, right? Times 10 to the 23rd. So I got 20 or 19 zeros tacked onto the end of that number. Okay? It was a big, big number. And it's a way for us to represent atoms, right? Because we have a lot of atoms. It's a way for us to represent atoms in a more realistic or, not realistic, I guess, a more manageable number. Rather than saying I have 6.022 times 10 to the 23rd atoms, right? I can say I have 1 mole. So it gives us a way to talk about large quantities of atoms in a more, an easier to deal with number. Okay? So 1 mole of something weighs the same, 1 mole of it in grams weighs the same as it does on its atomic level. So if I would ask for the molar mass of oxygen, you would tell me 16 grams. Okay? So that's saying 1 mole of our oxygen atoms, if I put it on the scale, if I put 1 mole of oxygen atoms on a scale, they would weigh 16 actual grams. Okay? But if I look at 1 single oxygen atom, it weighs 16 AMU. Okay, so molar mass and atomic mass have the same value, just different units. Okay, and they work on different scales. Okay, so You can find the molar mass of both elements and compounds. Finding the molar mass of an element is really, really easy. You just look on the periodic table. Okay, finding the molar mass of a compound is what we're going to deal with today. Is what we're going to learn how to do today. Okay, so the molar mass of an element is given on the periodic table. It's the same value as the atomic mass. So if I ask you what's the molar mass of sulfur, what are you going to tell me? Molar mass of sulfur. Go ahead, what is it? 32. Yeah. Close enough to round to a whole number. Okay. There's a lot of those first 20 that we can round to a whole number. Okay. Things that are really close to 0. So if they're a 0.97, 0.98, 0.99, or 0.01, 0.02, whatever. Out of those first 20, if you look on your periodic table, out of the first 20, ones that cannot be rounded or that I don't like to round are lithium, beryllium, magnesium. That's pretty much it. I don't deal with the noble gases much, so I don't really care about those. Chlorine, we don't round. Almost everything else can be rounded to a whole number. Okay? And boron, but we never use boron, so. Otherwise, in those first 20, almost everything can be rounded. Okay? That will be really useful today when we're looking at molar mass. Okay, like I said before, the units for atomic mass is AMU. The units for molar mass are called grams per mole. Grams per mole. So what that's saying is that it weighs X number of grams in 1 mole of our substance, right? That's the numerical value. So that's why the units are grams per 1 mole. Okay, that's really important to know the difference between those two. Atomic mass means we're looking on the singular atomic level, one single atom. Molar mass means we're looking at a much larger number of those atoms, and it's how many grams are in that mole. Okay, so for example, there's carbon, right? The atomic mass of carbon is 12 AMU. The molar mass of carbon is 12 grams per mole. Okay, for elements themselves, it's really easy to find molar mass or atomic mass because it comes right off the periodic table. Okay, but today we're going to focus on finding molar mass of compounds. Okay, you need to make sure that you understand the difference in the units. So if I ask you for atomic mass, you would label it AMU. If I asked you for molar mass, you label it grams per mole. Okay? Question so far? Everyone knows what AMU stands for? Atomic mass unit. Right, that should be a clue for you. That's what you use when you find atomic mass. Alright, so to find the molar mass of an element, we said was super easy. Look at the periodic table. But to find the molar mass of a compound, we need to take into account the molar mass of each atom in that compound. We're going to look at the compound water first, okay? How many hydrogen atoms do I have in a water molecule? 2 hydrogen atoms. Okay, so hydrogen atoms I have 2. What's the molar mass of hydrogen? 1, right? I can leave it at 1. Okay, so what's 2 times 1? 2. Okay, why did I multiply those 2 together? I had 2 hydrogen atoms. If each of them weighs 1 gram per mole, right, I'm taking into account all of my atoms of that hydrogen in our molecule. So oxygen, how many atoms do I have? 1, right? I only have 1 oxygen atom, and it weighs how many? What's oxygen's molar mass? 16 grams per mole. So since I only have one of those oxygen atoms to take into account, I multiply 1 times 16 and I get 16. Then I add those two together. So to find the molar mass of my whole compound, I take the molar mass of each hydrogen atom and I add it to the molar mass of my oxygen atom. Okay, which gives me a molar mass for water of 18 grams per mole. So what that's telling me is if I took 6.022 times 10 to the 23rd molecules of water, and I put it on a scale, it would weigh 18 grams. All right, exactly. So if I counted out exactly that many number of atoms, of molecules, water molecules. If I counted out that many water molecules and I put them on a scale, it would weigh 18 grams. Okay? The easier way to do that would be to pour water onto a scale until it's at 18 grams, and then you know you have 1 mole of water. Right? You can work the other way. So if I needed a mole of water, I can't count out individual water molecules. Right? It's not happening. So the way to do that is to say, I know that 1 mole of water molecules weighs 18 grams. So I set up my scale. I pour on 18 until it says 18 grams, and then I know I have 1 mole. Right? That's the way that we can do that. Any questions with how we calculated that molar mass? Take into account your mass of hydrogen altogether and your oxygen altogether, and then you add them up. Okay? All right, let's try another one here. Blah, blah, blah. Okay. Let's try one before we get to that. All right. Let's see, I want the molar mass of... This is called magnesium carbonate, MgCO2. Okay, magnesium carbonate. How many different atoms do I have here? I have 3. This isn't C with little o, right? That's carbon and then oxygen. So, how many magnesium atoms do I have? I have 1 atom, and it weighs what? 24.3 is where I usually keep magnesium. Okay? So that means that's 24.3. How many carbon atoms do I have? 1 carbon atom that weighs 12 grams per mole. So that equals out to 12. And I have how many oxygen atoms? 2, and they each weigh 16. Okay, so 16 times 2 is 32 grams per mole. Then I'm going to add all of those together. Okay, do we agree there? This 2, right here, only applies to what atom? Only applies to oxygen, so it only carries over to oxygen. Okay, it's really important. When you have a subscript, it only applies to the atom directly next to it, right? Directly to the left or directly before that. Okay, we're going to deal with atoms that or molecules that have parentheses here in a second, but otherwise your subscript only applies to the element directly to the left. Okay. Any questions with how we came up with any of these numbers? Okay. Let's try a couple more on your own here. Let's do these 2 on your own. Okay, you have 2 different compounds here, and I want you to find the molar mass of each of those compounds. First one is called ammonium nitrate. Second one's called sodium phosphate. Not that you need to know that yet. "56 grams per mole." Raise your hand if you agree. Okay, that's okay. Anyone have anything different? What'd you have, Clayton?
I got 80 grams.
80 grams per mole. Raise your hand if you agree. Okay, so what were we missing here on this first one? Maybe this other nitrogen? Possibly? I don't know. Okay, let's see here. Could have just been a math thing, okay? We had how many nitrogen atoms? 2 nitrogen atoms. So I should have taken 14 times 2. 28 plus 4 hydrogen atoms. Plus 3 oxygen atoms, which is 48. And we get 80. Okay? Okay. Next one. Jameer, what'd you have? Okay, that's okay. Paulina, what'd you have? 164 grams per mole. We agree? 164. Okay, we had 3 sodium atoms, which is 23 times 3 plus 31 plus 4 times 16, which is 64. So 164 grams per mole. Okay, very good. Any questions with those two? All right, now we're going to add one other step to this. If we have elements, or not elements, I'm sorry, if we have compounds with parentheses. Okay, we have compounds with parentheses that include numbers outside those. So it looks something like this. Fe2SO4 parentheses 3. Okay? So if we have compounds with parentheses and numbers outside, you don't have to necessarily write this down word for word. You need to know how to do these. Okay? So the number outside the parentheses multiplies everything inside. So it's kind of like this 3 gets distributed through those parentheses. You multiply those things. You do not add those together. Okay, so if I have an iron, this molecule is called iron sulfate. Okay, and I'm going to draw something that's really not chemically correct, but I want you to get a picture of what's happening in this molecule. You have 2 iron atoms that are maybe bonded to each other. And then here it's bonded to SO4, and it's bonded here to SO4. Right? This is telling us that we need 3 of these SO4 molecules. So this is not a chemically correct way to draw this, but I want you to envision what's happening, right? I have 2 iron atoms, right? Fe2, 2 iron atoms, and then I need 3 of these SO4 molecules. Okay, so that's what's happening there. That gives you a better picture on how many of each type of atom we have. Okay, so no, this is not a chemically correct structure, but I want you to see kind of how this might be happening. Okay, so if we're talking about the number of atoms, how many iron atoms do we have? Sorry, I'll erase this stuff so you can see it again. How many iron atoms do we have? 2. How many sulfur atoms do we have? How many sulfur atoms? 3, right? In this molecule, I see 1, 2, 3 sulfur atoms, right? This is just a picture of this molecule. So I have 3 of those because the 3 right here gets distributed through that. So, right, if there's no subscript, we know there's a 1 there. So 3 times 1 is 3. How many oxygen atoms do we have? How many do you think? Not 7, but 12. We multiply that. Okay, so if we have 4 oxygen atoms here, plus 4 oxygen atoms here, plus 4 oxygen atoms here, that's 12. Right, does that part make sense? That's why I drew the picture for you. It gives you a little bit better idea of what's happening with that molecule. Okay, So now to find the molar mass, I take 2 iron atoms. The molar mass of iron is 55.85. Sulfur has a molar mass of 32. And oxygen has a molar mass of 16. So let's go ahead and find that molar mass of our compound. Okay, so as we start adding these up, what did we get for our final molar mass? Brody, what'd you have?
399.7.
399.7. Good. And what's our units here? Grams per mole. Grams per mole. Okay, 399.7. Did we agree with that? Okay, good. So if we put 1 mole of these compound or these molecules on our scale, it would weigh 399.7 grams. Okay. All right, I want you to try these on your own. I'm going to give you a different one here for this last. Try those 3 on your own. 169.8 grams per mole. Very good. Okay, did everyone have something in that ballpark? Right, I had 169.87, just depending on where you rounded silver at. But it was important to keep silver at least a decimal point. Don't round that to a whole number. So, good. Were we in at least that ballpark? Good. Okay, second one. Trey, what'd you have?
95.1.
95.1. Okay, are we in that ballpark? I had 95.3. Okay, I kept magnesium at 24.3. I kept chlorine at 35.5. Were we somewhere around there? That's chlorine, yeah.
That was like carbon and
Oh, sorry, nope. Cl is chlorine. Yeah, that's kind of tough. Sorry. Did a lot of you do that? Okay, sorry. Cl is chlorine. So that each chlorine was 35.5. That gives us 71 plus 24.3, which was around 95. Okay? All right, last one. Bailey, what'd you have? 310 grams per mole. That's what I had. Raise your hand if you had 310. Okay, raise your hand if you went 3 for 3. Good. Okay, on this one, let's see. How many calcium atoms did we have? 3. How many phosphorus atoms did we have? 2. And how many oxygen? 8, not 6. We had 8 oxygen atoms. So 8 times 16 there. So we should have had a total of 310. Okay? Any questions with calculating molar mass? That's a big, big deal. We're going to have to do that a lot, like the rest of the year. Okay, so calculating molar mass, this is a big one for us. Okay, the next thing we're going to do with molar mass is something called percent composition. So what does the word composition mean? Yeah, composition means what it's made of. Percent composition. So when we're talking about percent composition, it means we're going to find the percent or what our compound is made of based on its mass. Okay, so after we find the molar mass of something, we're able to find the percent composition of something, which might tell us it's 30% oxygen and 40% hydrogen and 30 whatever percent carbon. Right? That's what percent composition is. Okay, and so the way we find percent composition is we're going to compare the mass of the element to the mass of the whole compound. We take the part divided by the whole. But we can't find percent composition until we find molar mass. That's always the first step. So I want you to think first, not necessarily about percent composition, but if I wanted to find the percent of like what you got on your test, You wanted to find the percent of what you got on your test. What do? Yeah, you take your score, whatever you got on your test, divided by how many points the test was worth, right? If it was worth 100 and you got 80 right, you got an 80%, right? That's how you find the percent of anything. You take the part, and on your test example, the part you got right, divided by what it was worth, so divided by the whole. That's what you do for any percent. So you take the part divided by the whole. So we want to find the percent composition of sodium chloride. The percent composition of sodium chloride. When it asks for percent composition, that means we're going to find the percent of every element. Okay, of every element. If I would ask for what's the percent of sodium in sodium chloride, that means I'd only need to be looking at sodium. But if it asks for percent composition, that means I want what the whole thing is made up of. So I need to do every element. Okay? So the first step in finding percent composition is to find the molar mass. That's the first step. So that's why I taught you how to do molar mass first. First step is to find the molar mass of sodium chloride. Okay, so that's what you need to do first. So that's what you should be doing right now, is finding the molar mass of sodium chloride. All right, so I know that the mass of sodium chloride is 58.5, right? Is that what you got? 58.5 or 58.45, depending on where you rounded, right? It's not that big of a deal, but 58.5 roughly. So if I wanted to find sodium first, I want to find the percent of sodium chloride that is made up of sodium. It's not just 50% because there's one sodium atom and one chlorine atom, right? That's not how it works. We're looking at the mass percentage. So if I find the mass of sodium, what's the molar mass of sodium? 23. I take that divided by the total. Right? Within our compound there is one sodium atom, which weighs 23 grams. The total weighs 58.5 grams. So to find the percent of sodium, I take the part divided by the whole, and I get roughly 39.3%. Okay, did you see in your calculator it came out as 0.39316, whatever, blah, 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 right? To convert that to a percentage, what do? I move the decimal place or I multiply by 100. Okay, so you don't give it to me in the decimal form. You'll give it to me in a percentage form. So when I take 23 divided by 58.5, I got 0.3933 whatever. Okay, you can multiply that by 100 or you can just move the decimal place 2 to the right. So 39.3%. So it's not 50% because there's one of each. It's only 39% because sodium weighs less than chlorine. Okay, so I found the percentage of sodium, so it's 39.3% sodium. Now to find my percent of chlorine, I'm going to take the mass of chlorine divided by the total. Okay, so 35.5 divided by my total, and I get 60.7%. So I know in sodium chloride, 39.3% is sodium and 60.7% is chlorine. Okay, in every sample of salt I take, it's going to contain 39% sodium and 60.7% chlorine. Okay, what should be true of these two percentages? That's right, they should equal 100. They should add up to 100. So this is a way for you to check yourself. When you get to finish with a percent composition problem, you should add your percentages together. If they don't add up to 100 or really, really, really close to 100, you know you've got a problem. Okay, they should add up to 100%. In this case, they do, right? All right, very good. I want you to find the percent composition. So not just the percent of calcium. I want you to find a percent composition of this calcium nitrate. Ca parentheses NO3 parentheses 2. I'm going to write it a little bit bigger for you here. Okay, let me just clear the whole screen actually. So percent composition of CaNO3 2. What's the first step to any percent composition problem? Find what? Find the molar mass first. Number 2 is divide the part over the whole for each element. How many nitrogen atoms do we see here? Nitrogen has how many? 2. And oxygen has how many? 6. Good. 6, not 5. So 6 times 16. Yeah.
So for the ones that have 2 parts of them, we would take the whole amount they contribute to the molar mass divided by.
Correct. Yeah, good question. All right, so as we start looking at percent composition here, we need to take into account all of the calcium atoms and all of the nitrogen atoms and all of the oxygen. So if we look at calcium, we're going to take the part divided by the whole. So I take the single calcium atom, which weighs 40 grams, divided by 164, and I get about 24.3% calcium. Okay, do we agree with that part? Right, I take the part of calcium, which weighs 40 grams, and I divide it by the whole, which is 164. For nitrogen, do I have 1 nitrogen atom or 2? 2. So I can't just take 14 grams divided by the total because that won't represent all of my nitrogen atoms, right? The mass of nitrogen in this compound is 28 grams, not 14. So I take 28 divided by 164, and I get 17.1% nitrogen. And then the same thing goes for oxygen. I don't just have 1 oxygen atom, so I can't take 16 divided by 164. I have 6 oxygen atoms, so I take 96 divided by 164, and I get 58.05% oxygen. Okay, if I had done only 14 divided by 164 and 16 divided by 164, my percentages would be way, way off, right? I'm not taking into account all of the nitrogen and all of the oxygen. So you need to make sure you do that. Then if we add up our percentages, 58.5 plus 17.1 plus 24.3, I got 99.9%, okay, which is where we need to be, right? We want to be really close to 100%. So that's where we're at for our percent composition. Okay, so when I look at percent composition, it's by mass. Every sample of calcium nitrate that I pull should have 24% of it of calcium, 17% of it nitrogen, and 58.5% of it oxygen. Okay, that's percent composition. Yeah?
For the calcium, before you were 163,
Uh-huh.
the decimal point would be 0.2439. I just recommended it.
Yeah, that's perfect. I just missed that when I was doing it. 24.4% is really what you should have been in. That would have given you exactly 100% on your finalizer. So yeah, that's right. Okay, if I would say, what's the percent of calcium in calcium nitrate, you would only have to do this part. That would be the answer right there. What's the percent calcium? But if I ask for percent composition, that means I need each element. So if I ask for what's the percent nitrogen in calcium nitrate, you still find the molar mass, but you would just do this nitrogen part. So you just need to make sure you read the question. Okay, if I ask for percent composition, I want the whole thing. If I just ask for one element, then you have to do one element. Okay? Any questions with percent composition? Okay.